Welcome back. In the previous session, we have discussed the binary phase shift keying modulation technique, under which we have discussed the time domain representation in mathematical and graphical form, and signal constellation plot, and we have also studied generation and detection of BPSK modulation wave. Under the detection, we have discussed the architecture of coherent BPSK detector. Hence, in this session, we are going to learn the error probability of BPSK. As discussed in the earlier sessions, every digital modulation technique can be evaluated with some performance metrics. Those are probability of error, then is power spectrum, and bandwidth efficiency. So these are all the performance metrics which are all used to analyze the performance of a digital communication system in the presence of additive white Gaussian noise channel. Hence, we can start with the error probability of BPSK. We know that in BPSK, the binary data for binary data 1, S1 of t is transmitted, which is represented by root 2 EB by TB cos 2 pi FCT. And we know that phi 1 of t, orthonormal basis function phi 1 of t is 2 by TB into cos of 2 pi FCT. Hence, S1 of t can be represented as plus root EB multiplied by phi 1 of t. Similarly, for binary data 0, the transmitter will transmit the symbol S2 of t, which is 180 degree phase apart from S1 of t. So it will be represented as minus square root of EB phi 1 of t, where EB is the energy per bit and TB is the bit duration. And the transmitter is having two symbol sets, S1 of t and S2 of t, and depending upon the incoming binary data from the binary sequence, we can determine the transmitter is transmitting any one of these two symbols. And these symbols are having a correlation with the orthonormal basis function phi 1 of t, since the dimension used here is 1 and the number of symbol is 2. So there are two correlations between these two symbols, that is S11 and S21. S11 is nothing but plus square root of EB and S21 is minus square root of EB, and in the signal space constellation can be drawn by considering the plus root EB, which is representing the message point 1, that is S11, the transmission of S1 of t, and the point in the signal constellation map, that is minus square root of EB, represents the message point for the corresponding binary data 0, and representing S21, which intimates the transmission of the symbol S2 of t. And there will be a threshold that should be used in the receiver in order to compare with the received vector. Let the received vector is R, then the lambda is representing the threshold value. It is compared with R. And the lambda is chosen in such a way that S11 plus S21 divided by 2, that is the average of all the energy values. So, or all the message points. So, S11 plus S21 divided by 2, which will provide 0. That is plus square root of EB minus square root of EB by 2. That will be equal to 0. So, lambda is equal to 0. So, this will be the threshold if the received point occurs in any of these locations, that is such a way that R is greater than lambda. Let R, we can consider the R is present in here. If R is greater than lambda, then the receiver will decide in favor of 1. If R is less than lambda, then the receiver will decide in favor of 0. This constraint is coming from the fact that in noise-free environment, we can define R is equal to either S11 for the transmission of binary information 1, or R is equal to S21 if the binary data transmitted is 0. So, R will be specifically plus root EB when 1 is transmitted. Similarly, R is equal to S21, that is minus square root EB when 0 is transmitted. This is in the case of noise-free environment. But in the presence of additive white Gaussian noise, R will be equal to S11 plus N, that is plus root EB plus N. So this is when 1 is transmitted by the transmitter. If the noise N is positive, then constructive addition will happen. If the noise, additive white Gaussian noise amplitude is negative, then destructive addition will happen. If in the case of constructive addition, R will be located here. If this is the space of N, then R will be located plus square root of B plus N. Suppose if N is having constructive addition. If n is positive, this will occur. If n is negative, then R will be located here in the case of when 1 is transmitted. Similarly, on the other hand, when 0 is transmitted, R is equal to S21 plus N. So, minus square root of EB plus N. Here also N may take two values. If N is positive, then R will be located here. If N is negative, then R will be located here. So during the transmission of the binary information 1, if N is positive, then we need not to bother about it, because the rule is in such a way that the decision rule has been taken. If R is greater than lambda, then the decision will be taken in favor of 1. Similarly, if the binary data 0 is transmitted by the transmitter and the additive white Gaussian noise is having a destructive addition effect in the signal, then we need not to bother about it, because the decision rule is for deducting the binary data 0 is R less than lambda. So it will decide in favor of the binary data 0. But when the transmission of 1, if the noise is negative, and in another case, the transmission of binary data 0, if the noise is positive, depending upon the amplitude of the noise, there is a possibility for this R to cross this boundary. Similarly, this R will cross the boundary and will located on the another region. So this, at this time, if the R is crossing the boundary during the transmission of 1, if the R is located here, then R will be less than lambda, but the binary data 1 is transmitted. But the receiver will decide in favor of 0. Similarly, if the binary data 1 is transmitted, but the R is lying on the region Z1, that is R is greater than lambda. Actually 0 has been transmitted, but the receiver will wrongly decide as the binary data 1. So these are all the erroneous conditions. And this will occur when the amplitude of the noise is greater than the amplitude of the signal point or the correlation value in both the cases. So to have realizing this decision making process in the presence of additive white Gaussian noise for correct deduction, we can determine the decision rule for symbol 1 and symbol 0. The decision has been split into two regions based on the threshold value, that is lambda is equal to 0. By considering the region 1 where lambda is greater than 0, and by considering the region Z2 where lambda is less than 0. And the region Z1 is the locations for deciding it in favor of 1, and region Z2 is the region for the received binary informations to decide it in favor of the binary information 0. And the region Z1 is extending from 0 to infinity. Region Z2 is extending from minus infinity to 0. The decision rule has to be framed in such a way that the receiver has to decide the signal S1 of t for the corresponding binary symbol 1 if the received signal point falls in the region of Z1. Similarly, the receiver has to decide the signal S2 of t for the corresponding transmitted binary information 0 if the received signal points are located in region Z2. There are two erroneous conditions may occur during the presence of additive white Gaussian noise at the receiver end. The case 1 is actually the signal 0 is transmitted. The signal corresponding for the binary data 0 is transmitted, but the receiving point, the received signal point will be located on region Z1, so the receiver may decide it in favor of the binary data 1. That is, it is considering S1 of t has been transmitted wrongly. On the other hand, if the binary data 1 is transmitted and the corresponding signal S1 of t is transmitted by the transmitter, but the additive white Gaussian noise is present in the system in such a way that the receiver signal point will located on the region Z2, so that the receiver will decide wrongly in favor of the binary data 0 by considering that the transmitter has transmitted the signal S2 of t. So let us start the overall error probability calculation. We can start with the probability of error when the symbol 0 is transmitted, but the received signal point or the observation point is occurring in the region of Z1, that is between 0 to infinity. And we know that the received signal R of t is nothing but S of t plus N of t. Originally, what has been transmitted is S1 of t. But here we are considering that S2 of t is transmitted because 0 is transmitted. 0 is transmitted, but receiver is deciding it in favor of S1 of t. Hence, it occurs in the false region, that is region Z1 between 0 to infinity. And we know that R is determined by the integral of R of t phi1 of t dt over a period of tb, and the conditional probability density function of a random variable R, given that the symbol 0 was transmitted, is defined by f R of R given 0, that will be equal to (1) divided by square root of pi n naught multiplied by exponential of minus R minus S21 the whole square by n naught. This is achieved by considering the additive white Gaussian noise which is having a mean value of 0. And the variance or the power spectrum as n0 by 2. And we know that the Gaussian spectrum f of n can be represented as 1 divided by square root of 2 pi sigma n square multiplied by exponential of minus n minus mu the whole square divided by 2 sigma n square. So instead of sigma n square, we can substitute n0 by 2. So 2 will get cancelled. So we can write one divided by square root of pi n0 and exponential of and mu is equal to 0. Mu is equal to 0. So it can be represented like this. And R can be represented as S. For this transmission case, it is S21 plus N. Because S2 of t has been transmitted, so that S21 plus N. So S21 is a deterministic signal which is having an amplitude. The probability of S is lying at minus square root of EB, and it is occurring for only one time. And whereas the additive white Gaussian noise f of n is added here, which is having a 0 mean. So the bell-shaped curve is centered around 0 volts. Hence, f of r can be defined as if both the amplitudes are added. So square root of EB plus 0, then it will occur at minus square root of EB. So now f of r is also distributed by Gaussian, which is centered around minus square root of EB. Hence, f of r can be defined as f r of r when given 0 is transmitted, it follows the same Gaussian distribution, exponential of minus, the variable is r here, and the mean is minus square root of EB. Because always in the Gaussian distribution, the maximum value of the Gaussian distribution occurs in the mean, at the mean value. So it is minus S21 by N0. This is what is written here. And we know that S21 is equal to minus square root of EB, so we can write R plus square root of EB the whole square by N0. This is the conditional probability density function. Hence, the conditional probability of the receiver to decide in favor of 1, then the region is between 0 to infinity. Hence, to determine this conditional probability, P10 is conditional probability for transmitting, for receiving 1 when 0 is transmitted is determined by the integrating the conditional probability density function within the region of 0 to infinity. So it can be represented as integral of fr of r given 0 dr over the time interval between 0 to infinity. Now, the function of fr of r is substituted here. And here we are going to consider u is equal to r plus square root of n naught. And if you differentiate this function u, du will be dr by square root of n naught, and dr will become square root of n naught into du. And applying these values in the limitations, the limit 0 to infinity is changed from square root of EB by n naught to infinity. That is, here r is by changing the integrating variable, the region r from 0 to infinity is changing in such a way that the integrating variable u within the limitations from square root of EB by n naught to infinity. Applying all these values in the above expression, the conditional probability for receiving the binary information 1 when 0 is transmitted is given by P10 is equal to 1 divided by square root of pi. Here, instead of dr, I am going to substitute square root of n naught into du. So this square root of n naught and n naught will get cancelled. So 1 divided by square root of pi alone will be left over as a constant. And the 0 will be replaced by square root of EB by n naught, and infinity will be replaced by infinity. And this entire term is replaced by u square. And applying all these changes, we will get this expression. And if we multiply 2 in the numerator and divide 2 in the denominator, we will have this expression. And this is nothing but error function of square root of EB by n naught. That is integral of x e to the power of minus e square du over a period from x to infinity can be represented as error function of x. By this way, this can be represented as 1 by 2 into error function of 2 divided by root pi. This term can be written as error function of s. Hence, this term can be written as 1 by 2 into error function of square root of EB by n naught. Similarly, let us consider the next case when the symbol 1 is transmitted, but the received signal point is lying on region Z2, that is from minus infinity to 0. Hence, the receiver can decide wrongly in favor of the binary symbol 1. That is case 2. Binary 1, data 1 is transmitted, but the receiver is receiving, or receiver decides receiver decides in favor of the binary data 0. Similarly, FR of R given 1, that is the conditional probability density function for the random variable R, that is for the receiving signal point R, given that the symbol 1 is transmitted, which can be written as 1 divided by square root of pi into n naught exponential of minus of R minus S11 the whole square divided by n naught, and we know that S11 is equal to square root of EB, which can be represented like this, and the conditional probability can be determined by integrating the conditional probability density function between the region minus infinity to 0, and P01 is the conditional probability for receiving the binary data 0 when the binary data 1 is transmitted. The 0 is deducted in the region Z2, that is from minus infinity to 0. That is why the integration limits are from minus infinity to 0. By applying the value here and assuming that u is equal to R minus square root of EB by square root of n naught, and the limitations, changing the limitations and applying here, we will again get P01 as, sorry, this is P01. P01 as 1 by 2 into error function of square root of EB by n naught. So, as the symbols are equiprobable, 1 and 0 are assumed as an equiprobable symbols, P10 is equal to P01. Hence, the average probability of symbol error or bit error rate is given by the average function, which can be represented as P01 plus P10 divided by 2. Both are having the same function. So it is again having PE as 1 by 2 into error function of square root of EB by n naught. And the average probability of symbol error is directly proportional to the bit energy for a fixed value of n naught, where n naught is the noise power spectral density, or the power of the noise per unit bandwidth. If the bit energy is increased, if the energy per bit is increased, then the Euclidean distance will get, if the square root of EB is increased in the signal constellation plot, then square root of EB and square root of minus EB are very far away. The distance d will be large. If EB is large, then the Euclidean distance will be large, so that the signal to noise ratio will also be improved. And here the EB by n naught is nothing but energy to noise ratio. This plays a very crucial point. It plays very important role in deciding the probability of error. Hence, if you plot EB by n naught versus the probability of error or bit error rate, then as the energy to noise ratio is increased, or signal to noise ratio is increased, then the probability of error will get decreased. Since the Euclidean distance between the two message point is getting increased. Generally, EB by N0 is measured in dB. If EB by N0 is equal to 0 decibel, then in linear scale, EB by N0, that is log of EB by N0 is equal to 0 decibel, then EB by N0 is equal to 1. So EB is equal to N0. That is at the point 0 decibels, it will have the maximum probability of error, and it is expected that it will attain the 0 value when EB by N0 increases up to infinity. But this will not happen, and we cannot have such a kind of ideal systems. So we can able to tolerate some number of bits in the overall received symbols. That is, if the probability of error is 10 to the power minus 4, then it is tolerable. That is, if 1 bit is error when 10,000 bits are transmitted, then we can say that particular transmission is good enough.